Chem 106, Chapter 21, Nuclear Chemistry, Lecture 2. Continuing on page 4 of the outline, Section 5, Detection of Radioactivity. When radiation strikes ordinary matter, it causes it to be ionized, so it gains an electrical charge. So scientists Geiger and Mueller, I don't know what happened to Mueller's name off of the device now, but now we all just call it a Geiger counter, but it used to be a Geiger-Mueller counter. But so either way, a Geiger counter determines the amount of ionization by detecting an electric current because, again, ionization, charged particles, electrical current flows from that. And so on the Geiger counter, the probe part of it is a thin window, and the ionizing radiation penetrates that and causes the ionization of argon gas. So even though argon is a noble gas, it can still be ionized by radiation. And once those particles of argon are ionized, they then strike a detector at the other end of the probe, so the front end has a window. If you put it in the presence of ionizing radiation, the argon inside becomes ionized, and that strikes the detector at the other end, and so it causes that staticky sound that you hear if you've ever been around a Geiger counter or seen it on TV or any of that stuff. It makes this staticky little sound. And so the more radiation, the more staticky sound it makes. And so you can get an idea auditorily how much radiation there is. But now even if you had a Geiger counter sitting there doing nothing, it would still make a fuzzy little click every so often because there is radiation all around you called background radiation. And we'll get to that later in this lecture, but I just want you to know that even with a Geiger counter on, it's not broken, even though it's making these staticky clicks every so often. That's because it's detecting the background radiation that's around you all the time. Okay, so another method of detection employs an instrument called a scintillation counter. A substance is called a phosphor. Remember, like from phosphorus, it means it glows in the dark. A phosphor is allowed to interact with radiation. Light is produced, that's what it means. It glows. Phosphor it glows. And so light is produced when radiation strikes a suitable phosphor, and so we can count those photons. So the light is detected and used to quantify the amount of radiation, the number of photons striking a detector then generated from that phosphor. And so those are called scintillations, and so we can count them, so a scintillation counter. Radio tracers are used to follow an element through a chemical reaction, whether it be a regular chemical reaction in the laboratory or complicated physiological reactions in medicine. Carbon-14, of course, has been used to study the chemical pathways in photosynthesis, for example. And other ones, we're going to talk about, like radioisotopes used more commonly in medicine here, or in the house. Americium-241. That radioisotope is used in smoke detectors. What it does is, how a smoke detector works is you have the americium-241 on one side of a hole, and it's going to emit radioactive particles that strike a detector across that hole. So you've got the radioactivity passing across this gap from emission to detector, and so long as the detector keeps detecting the radioactivity, all is well. But if you have a fire and therefore smoke comes up and interferes in that gap so that the radioactivity begins to diminish as it goes from emitter to detector. It is interrupted. And so whenever that pathway is interrupted by smoke, that's why we keep them up on the ceiling. If that pathway is interrupted by smoke or dust or whatever, that's why dust will set them off as well, it'll cause the smoke alarm to sound if you interrupt that pathway. So americium is the radioactive isotope used in smoke detectors. Cobalt-60, as we mentioned in the first lecture, is used in cancer treatments. Iodine-131, treatment of Graves' disease, which is hyperthyroidism. Very interesting pathway for that, because iodine is only used one place in the body, and that's in the thyroid. So all iodine that goes into the body concentrates in your throat at the thyroid gland. And so we can use radioactive iodine to kill part of the thyroid when it's in a hyper mode. And so what'll happen is they tend to give too much of the iodine 131, so now the thyroid function is less than optimal, and so the person spends the rest of their life taking synthetic thyroxine, which is called Synthroid. So medicine's not perfect. Technetium, the how you really say it is technetium 99, most widely used radioactive pharmaceutical for diagnostic studies in nuclear medicine. So if anybody's going in there, really become really familiar with technetium 99. And then, of course, there's thallium 201 for nuclear cardiology and tumor detection. And here's the bad part for you, is that of course there's a more comprehensive list that's located in the Chapter 21 folder on Blackboard, and you are responsible for knowing the applications of the various isotopes. What are they used for? Because any of them are fair game for the exam. So you need to get that handout and memorize where the isotopes are used, because any of it is fair game for the exam questions. So make sure you get to that and do that in a timely manner. Section 6, energy and nuclear reactions. Of course, we have a good old equation, E equals mc squared. Einstein showed that mass and energy are proportional to each other, and then we have this constant of proportionality to make this an equal sign. So c squared, the velocity of light in a vacuum squared, is a really large number. And so small changes in mass can cause a large change in energy. And so mass and energy changes in nuclear reactions are much greater than in chemical reactions. It doesn't take much mass to destroy a city. And even with nuclear reactions, you're talking only somewhere between 2 and 10% conversion of mass into energy. And on the low side, 2 to 3% conversion of mass to energy wipes out 100,000 people in the blink of an eye. Closer to 10% conversion of mass to energy wipes out millions of people in the blink of an eye. So, not always great things as the result of science. People use them for potentially terrible things. Not to get into the political side of it, it's just still, regardless of the reality, it is a terrible thing when science is used to wipe out life. All right, enough of that. Fission. Heavy nuclei gain stability by splitting these things into smaller nuclei, and the process is called fission. So if we take a heavy nucleus that's radioactive, split it into smaller nuclei, and give them stability, then that is the fission process, the splitting and fission. So make sure, again, the exam is pretty heavy with definitions and all. So make sure you know the difference between fission and fusion. Fission is the splitting apart, and fusion will be the putting together, the making them stick together. All right, but nuclear power plants traditionally and most forms of nuclear weapons still utilize fission, and those are the smaller weapons. Those are the ones that only wipe out hundreds of thousands of people at a time, not millions. And power plants, and that's why with fission, the fission products usually still are radioactive as well, even though they're a little more stable. They're still radioactive, and so all this waste that these nuclear power plants generate is still going to be what we call hot. It's going to be radioactive for thousands of years, and so storing it where it won't hurt anything is nearly impossible. And so that radioactive waste, is dangerous to handle, transport, and store. And they're talking about using a mountain out in the western United States to store a lot of it. But of course, if you're on the eastern seaboard, how are you going to get it from the eastern seaboard to the western mountain storage facility? And normally they go by rail car and all that, but people find out and have protests. It's like, no, you're not putting that train through our town. So it all turns political again. And so the whole thing about all this medical waste, from nuclear power plants, from nuclear medicine at hospitals, most places just end up storing it on site, and they end up storing it not in very stable containers. And if there was ever an earthquake or anything like that, all of this nuclear material gets out into nature again, especially if it hits a water table. So it's a real disaster in the making. It's an environmental disaster that could happen at any time. So fusion is a much better way to go. But whereas fission, even though it was really technical and complicated to figure out how it works and all, fusion is exponentially more complicated. Sounds easier, but it's much, much harder to do fusion than it is fission. And honestly, it's so much cleaner to do fusion, but we don't know how yet. We're almost there, but not quite. And so with fusion, you're going to take light nuclei like deuterium, which is an isotope of hydrogen, and fuse them together to make helium, which is the most stable element there is. And so if helium is your only waste product, then you're really, really onto something because the world needs more helium anyway. And so the process is called fusion. And fusion products are not radioactive, so this is a good energy source and tremendous energy source. But you need at least 40 million Kelvin to start a fusion reaction, and that's a little difficult to happen here on planet Earth. 40 million Kelvin is very difficult to achieve. And we call these thermonuclear reactions because it takes so much thermal energy in order to get the nuclear reaction to happen. But thermonuclear applies only to fusion, not to fission. It doesn't take heat energy to do fission. We just have to put the nuclei together, basically. These heavy nuclei, put them in the right environment, and it goes. But fusion, in order to get it started, requires 40 million Kelvin to happen. And so weapons based on fission are just what we say atomic weapons, but weapons based on fusion technology. See, a fission reaction, a fission explosion can get you 40 million Kelvin, and so therefore that's why the fusion weapons require fission. So there's still radioactivity. So thermonuclear weapons, the ones that wipe out millions of people at a time, still require a fission core in order to gain the 40 million Kelvin in order to have the deuterium fused to helium as a fusion reaction, which is so much more energetic. Again, the bad sides of it. So if we can do fusion without the necessity of a fission core, then we're really going to have a great, almost endless source of energy with no waste products except for helium, which we need anyway. But fusions are referred to as thermonuclear. So make sure you keep those terms straight. Section 7, radiation in the environment and living systems. So again, radiation is ionizing. So when that occurs, radiation is going to remove an electron from an atom or molecule from its valence shell, creating a charged particle. And so most ionizing radiation interacts with water and tissues and forms the H2O plus radical. That's not good, because then those H2O plus radicals interact with other water to make acid and then the hydroxyl radical. Notice there's no minus here. That's not a typo. There's no minus. It makes acid and what we call a hydroxyl radical. That hydroxyl radical is very reactive and will cause lots of tissue damage. Radicals are capable of causing substantial damage in biological tissues by unwanted chemical reactions. Again, those of you going on to organic, at the end of Organic 1, we will talk about radical reactions, and you'll get a better understanding of how those work, and then hopefully potentially can see physiologically, wow, that's not a good thing to have radical reactions happen. Physiologically, whenever radical reactions do happen, because some of them are necessary, such as vasodilation and constriction, radicals are generated to help dilate the blood vessels and all, but molecules are standing by on purpose to destroy those radicals. When they're made, do their job, then they're destroyed. So these antioxidants keep radicals under control under normal conditions. But whenever you have an external influence, those hydroxyl radicals, there's no natural mechanism to control them, so they do a lot of damage very quickly. Radiation doses. So absorbed radiation is measured in various ways. So a gray, 1 GY, is the SI unit for absorption of 1 joule of energy per kilogram of tissue. So 1 joule per kilogram of tissue is called a gray. A rad is the radiation absorbed dose. RAD, rad. It doesn't mean radiation, it's the radiation absorbed dose, and that's equal to the absorption of 0.01 joules per kilogram of tissue. So 1 gray is equivalent to 100 rad. Now, because not all forms of radiation have the same effect, we correct for the differences using the RBE, the relative biological effectiveness. The RBE is about 1 for a beta emission and gamma radiation, and 10 for an alpha radiation. A REM, the Röntgen equivalent for mass, REM, Röntgen equivalent for mass, is rads times RBE. The SI unit for the effective dosage is called the sievert, 1 SV, which equals 1 GY, which of course then equals 100 rem. Okay, now you're not doing any calculations with this, you're just knowing terms. You are not going to do any calculations of how many rems or rads or sieverts or grays or anything like that. This part's qualitative. I just want you to know the terms. And the average annual exposure to all sources of ionizing radiation, as I told you about background radiation, there's uranium in the soil, and then there's radon that's produced as one of its products of decay, and so on. So all around us is natural radiation, and those of you that fly on a regular basis in jet airplanes, when you go up 30,000 feet above the surface of the Earth, you're exposed to a lot more ionizing radiation in that part of the atmosphere than you are here at the surface. So people who fly a lot are getting a lot more radiation than those of us who tend to stay on the ground a lot more. But your average annual exposure from all natural sources of ionizing radiation is about 360 millirem. So that's not a whole lot. It's not free of radiation, so you're getting damaged a little bit all the time. But the natural sources all add up to about 360 millirem. And so you should know that kind of detail as well. Radon. Radon is the natural decay product of uranium-238. Even though it's a noble gas, it itself is not chemically reactive, but it's radioactive, so its nucleus is still emitting radiation. So radon, noble gas, not chemically active, but it certainly is nuclear reactive. And so radon exposure accounts for more than half of the 360 millirem annual exposure that people have. And, radon builds up. So, just as a last thought here, if you have a basement that is completely underground and very little in the way of windows, radon is building up in those spaces because the uranium is in the ground and it's decomposing as one of its products is radon. And so radon tends to accumulate in those spaces like basements that are completely underground and with limited windows. And so if you spend any time in those kind of situations, you need to get a radon test kit and have that area tested so you can figure out how to get all the radon out of there if you spend any time in there at all. If you have a basement that is a walkout basement or has substantial amounts of windows that are open in particular, so there's lots of airflow, then there's not as much worry because the radon is going to be continually swept out with the airflow as well. But if you have a basement space that is used a lot, that has limited airflow, like, it's completely underground and limited windows, so they're not open and all that, then there's probably a good chance that the radiation or the radon levels are very high, and so you're being exposed to more radiation, background radiation, than you should be. So, and that can cause various kinds of cancers. So get a radon test kit if that's the situation you're in, and get it tested to see and help remediate any risk you have there. This concludes Lecture 2.